All right, we're going to get started here in just a minute, you guys. Hopefully you guys can all hear me and I'm coming through good. I'll answer any questions. I also have some other sample questions so that if you guys want me to say like, hey, do like a wave calculation or something like that, I do have some sample problems I can go over as well that might be a little bit new. So I do have a list of some other problems that we can work on. So we'll get started here. We have about an hour. Any questions to start us off? Go over to, can you guys actually type out some of the problems? Or I could try to grab my iPad and look at the problems. I just don't have worksheets out in front of me right now. So actually, let me see if I can grab my iPad and pull up some of these problems so you guys don't have to type them all out. Probably be a little bit easier. All right. Give me a minute to bring this up. Sorry, guys, my iPad's a little bit slow. All right, so 5.1, that homework, bringing it up. All right, so let's start with 5.1. I have 5.1, number 2. So this is worksheet. Try to keep my colors in order. 5.1, number 2. So this problem says microwave radiation has a wavelength on the order of 1 centimeter. Calculate the frequency and the energy of a single photon in this radiation. All right, so the first thing is if we're given 1 centimeter, since it's in meters, we're going to assume that it's our wavelength. It also says that it's our wavelength, so we need to first convert this into meters. So whenever we're doing this, we do have to convert things into meters. So if we convert this into meters, what we find out is that it is equal to 10 to the negative 2 meters equals 1 centimeter. So what this ends up equaling is 0.01 meters. So now that we have that converted, now we could plug this into our equation. So there's a couple equations that we're going to use. I'm going to make these nice. I'm going to make these orange so we can read them and make them nice and clear. So what we see is that we have 2 equations. We have that the speed of light is equal to the wavelength times our frequency. And then we have the equation that the energy of our photon, or energy, is equal to h, which is Planck's constant. You'll be given this on the test, times our frequency. We could rearrange this equation, and if we plugged in what wavelength is, we could also kind of get this other equation where it's h times c divided by lambda. But we don't have to use that one. Okay. So let's first look at this problem. So the first thing that we need to solve for is our frequency. So divide both sides by lambda. What we end up getting is the constant, the speed of light, divided by our wavelength equals our frequency. Our speed of light is 3.00 times 10 to the 8th meters per second, divided by 0.01 meters. Units cancel out. Notice that my units end up being inverse seconds, which is the same as a hertz. So plug this into your calculator. I want to make sure that I plug this in correctly. Make sure you guys are comfortable using, again, your exponent button on your calculator. One of the reasons why I always suggest, and why I suggest at the beginning of the year, that you guys get your own calculator is because all calculators are slightly different and the exponent button looks different on all of them. So what this ends up being is 3.00, I didn't leave myself enough room, times 10 to the 10th. And again, that's inverse seconds or hertz. Now what we can do is that we could now plug this into this equation. Now that we know frequency, I'm going to go ahead and use this equation just because obviously there's a lot fewer variables, so less room for error. So now we can solve our energy. Energy equals Planck's constant, and you know what? I'm not going to be able to write that whole thing there. Let's see, 6.626 times 10 to the 34th joules times a second. Oh, I shouldn't have done this way. I'm going to put this down here, times our frequency, which is 3.00 times 10 to the 10th, and that's inverse seconds. You notice that your units of seconds cancel out, and so we will end up getting joules. So if you multiply those together, 6.626, 10 to the 34th, and we multiply that by 3.00, 10 to the 10th, we end up getting the energy to be, let's do two significant figures since our original problem had two significant figures. So that would actually be 2.0 times 10 to the 45th joules. And so there is my answer. Okay. Some complicated wave calculations. This is probably as complicated as it's going to get, Nicholas. Let me know if you want me to go over one that's a little bit more complicated. But I mean, having to solve both of these would probably be as complicated as it gets. You also do want to know that a lot of the times they will give you your wavelength in nanometers. And I think we might look at one like that in a minute. No. So if you're given the problem in nanometers, just remember that 10 to the negative 9th nanometers equals, excuse me, not 10 to the negative 9th nanometers. 10 to the negative 9th meters equals 1 nanometer. So that would be your conversion right here. But that's pretty much as complicated as it's going to get with these problems. Let's look at 5.1, number 4, which is the next requested one. So this problem says it takes 7.21 joules, or 7.21 times 10 to the negative 14th joules of energy to remove an electron. Okay. So we're given energy, and we are told that it's blah, 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 blah. Let's try to actually write. I don't know if you guys have noticed this, but sometimes what I say does not match what I write on the board. 7.21 times 10 to the negative 19th joules. So that's energy to remove an electron. So that would be our ionization energy. What is the maximum wavelength that this light can produce? So what does that mean? It means that given energy, we want to find wavelength. If we're trying to find wavelength, the only equation that we have that actually has both of these, I had on the previous slide. So it's going to be energy equals Planck's constant, C, wavelength. Rearrange this equation to solve for this. So what we end up getting is wavelength equals H times C divided by energy. Now, you could always double check to make sure that your answer is right by paying attention to your units. So let's go ahead and plug everything into this equation right here. So we're given that our wavelength equals H, which is a constant, 6.626 times 10 to the 34th joules times a second. times the speed of light, which is 3.0 times 10 to the 8th meters per second, divided by the energy that we were given. So the energy that we were given was 7.21 times 10 to the negative 19th joules. So our wavelength should be in meters. So we should be left with meters, which if you cancel out your seconds, you cancel out your joules. Hey, look at that. We get our units that we want. So now you want to make sure that you plug this in correctly. So I'm going to plug this into my calculator. I don't have any answers in front of me. So 6.626 to the 34th. And we're going to multiply that by 3.0 to the 8th. And then we're going to divide that by 7.21 times, whoops, I just made a mistake. Hold on, you guys. 626 to the 34th. And we're going to multiply that by 3.0 to the 8th. And then we're going to divide that by 7.21 to the negative 19th. This is going to be a huge number. Someone maybe check my math, because since I don't have the answers in front of me, but this is a huge number. Our original had 3, so 2.76 times 10 to the 61st meters. Why do I feel like that's wrong, you guys? That seems like a huge number. Negative 34. Thank you. Did I make a mistake on the other one too? That would make a huge, huge difference. I don't know why I put 34. Yeah. That makes a huge difference. Okay, let's recalculate. I did done goofed. Thank you, Aiden. Okay, to the negative 34th. And then we're going to multiply that by 3 to the 8th. And then we're going to divide that. Oh, this answer looks better already. And we get, whoops, 2.76 times 10 to the 1, 2, 3, 4, 5, 6, 7, negative 7th meters. Awesome. Knew I did something wrong. All right, so there's that problem. All right, let's look. Can you explain atomic radius trend? Where's Miss Hoff? Can you guys not hear me? Or are you asking like, where am I like in location wise, like where I actually am? That'd be kind of weird. You guys can hear me and see everything, right? We're good? I'm not like talking to like no one. We can hear you. Good. Thank you, Augustus. All right. Let's talk about atomic radius trend. So if we were to think about our trends, maybe someone text Daniel. Maybe he's lost. Maybe we don't know where he is. Okay. It's not loading for you. Oh no. So if this is our periodic table, what we see, so this is atomic radius. What we see is that going across a period or across, what we see is that the atomic radius decreases. And as we go down, what we see is that atomic radius increases. Now, if we want to explain why, and the why is the most important part, is why do we see this? What we see is that going from left to right, what we're doing is that we are increasing. So I'm going to go period. So we're going across a period. We are increasing the number of protons in the nucleus. If we're increasing the number of neutrons, what that means is that there is a stronger attraction. Increased, we'll say Coulombic attraction, like that good vocab word, to the electrons. If that Coulombic attraction increases, what that means is that electrons are held more tightly. If they're held more tightly, that means that we have a decrease in radius. So that's our period going from left to right. We did talk about this, and we did kind of say another way to explain this is what I said as the Z effective, which is also called the effective nuclear charge. So this is kind of the proper name to describe why we see this trend. All right, going down a row, and I'm kind of running out of room on this slide, so let's go down a row. We see another one. As we go down a row, what we are doing is that we are seeing that electrons are adding in, adding in higher energy shells. Higher energy shells. So higher energy, I should put shells. Let me not put that. Let me put higher energy shells. These higher energies are further away from the nucleus, which means that the atomic radius increases. So we have an increase in the radius. So because those energy shells are further away and those electrons are occupying those atomic orbitals that are further away, therefore our radius increases. So that is that problem. Let me look at, let's see. Let's talk about suborbitals and orbitals. Okay. Let's talk about orbitals. Okay, so Daniel had a suggestion about orbitals. For example, what if we had, let's think about n equals 4. So n equals 4. This n right here tells you the electron shell, or you can think of this as the energy level. And since we have 4 energy levels, or we have 4 energy, since we have 4 energy levels, this tells us also that we're going to have 4 subshells. Subshells are the shapes. And when I mean shapes, I mean S, P, D, F, and then remember we could have like G, H, and further out. So since this is energy level 4, we're going to have 4 subshells. We're going to have the first 4. So we're going to have a 4s, a 4p, a 4d, and a 4f. So these are going to be the 4 that occupy this 4th energy. So these are our subshells. Within each subshell, we have orbitals. And the orbitals, you could think of the orientations. So the orbitals are how many p subshells, or how many orbitals make up this p. What we saw is that in a 1s, we only have 1 shape, and then each one increases by 2. So the p's, we have 3. In the 4ds, we have 5, and in the f's, we have 7. So that gives us a total of, here we have 4, 9, 16 orbitals. If we have 16 orbitals, we also know that there are 2 electrons per orbital. So we can only have 2 electrons in each orbital. So if we can only have 2 electrons in each orbital, this fourth energy level can hold 2 times 16, which says that it can hold 32 electrons. So that's the maximum number of electrons that it could hold within that energy level. Let's see what else. So what does it make the first one? Electron affinity. Okay, let's look at electron affinity. Electron affinity is referred to as energy release when an electron is gained by a neutral atom. That's kind of a mouthful, right? So what we have is we have a neutral atom A, it gains an electron, and when it gains that electron, it becomes an anion, and it releases energy. The more that this atom attracts this electron, the more energy it will release. So the more attraction this atom has, the more energy it will release. So we have a trend, and we have this idea of attraction. As we go from left to right across a period, this increases. And it increases for the same reason that our radius decreases. As we go from left to right, we have an increase in our Z effective, which again, or our effective nuclear charge, which then again just means we have more protons, which means we have a stronger attraction. If we have a stronger attraction, more energy is going to be released when an electron is added. If we go down, we see that our electron affinity decreases. And we see that it decreases because there is more shielding. So we kind of talked about this idea of shielding. We talked about the idea that if we have an atom, the more energy levels that we have, and here's my electron, the weaker that attraction is. So that attraction is a lot weaker when those electrons are further out. And that's called shielding. So we have like kind of like this idea where each layer shields this positive charge from the electron. So if we're adding an electron to this outer energy level, the further away that that energy level is from the nucleus, the weaker that attraction is. So if we have increased shielding, we're going to have a weaker attraction. And if we have a weaker attraction, that means that we're going to have a lower electron affinity, that it doesn't want that. And when you think of the word affinity, it's a strong, what's the word? To have an affinity for something is to have like a strong want to have it. So like I have an affinity to drink coffee every morning. I really like to drink coffee. There's a good possibility that every morning I'm going to wake up and I have coffee. So electron affinity is the idea that how likely is it that that atom is going to add an electron. And the more likely or the stronger the attraction is, the more energy is going to be released when it actually gains that electron. So hopefully that kind of helps you identify and remember that trend. Okay, I think I'm caught up on questions. So if you guys have more questions or want me to go over anything else, go ahead and type it in there. Wait a minute. Daniel, we actually did talk about those two energy formulas. So if you go back to the beginning of the equation, you will see that. You will see that difference between the two energy formulas. Aiden, what was your question? Blah, 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 blah. Aiden. Oh, is there going to be questions relating to emission spectra? With emission spectra, what you want to know is that you want to know that energy is released. And when it releases energy, it's a certain amount of energy, and that certain amount of energy relates to a color. So there's not going to be any, not too much on like the POGL, but can you explain why we have different colors? So for example, we have Roy G. Biv. Red is lower in energy, which means that electron didn't fall as far down, so less energy was released, versus violet, which has a higher energy, and so more energy was released. So just kind of that basic idea, but I wouldn't spend too much on it. Don't worry about that too much. More on Daniels in the order of n equals 5. The order in the n equals 5 in the energies. Wait, so there's a 5s, n equals 5. There's a 5th energy shell, and the 5th energy shell, because we've never gone over the, because we've only, Charlotte, I've actually talked about this before. So if we think about those energy shells, so if we have n equals 5, that means that we have 5 subshells, and we technically can go higher. So we can have this idea that we have 5s, 5p, 5d, 5s, and then, or 5f, and then we kind of have these other ones that aren't filled according to our periodic table, but there's kind of hypothetical ones. So now we have the 5, we'll call it G. So again, this is hypothetical. This is not on our periodic table. We just don't have atoms big enough to fill this orbital. So if we were to look at the number of orbitals that make up each of these subshells, they always increase by 2. So this is 1, 3, 5, 7. This would be 9. So we could add those all together. We see that we have 25 orbitals. And then since that's 25 orbitals, we can then have 2 electrons filling each, which would be a total of 50 electrons. So again, this is a hypothetical because this is not currently on our periodic table. We don't know much about this. We don't have an atom that has electrons that are this far out, but we could hypothetically have something like that. As we think about these energy levels, each energy level gets further and further away. So the n equals 1 is further away, the n equals 2 is even further, so on, so on, so on. Then when you want to think about energies, you want to think about how they lay out on the periodic table. So to really understand the energies, the best way to do is look at the periodic table and write your electron configurations based off of that. For example, Ds are always lower than the S's for our energy level. So for example, if we have 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10. I think I said lower, but I meant higher. So this one is higher in energy, but it's still in the third, so it's still closer to the nucleus than this 4s. And then we could have 4p6 and so on. So just note that this one is kind of the outlier, that these go in order of energy, but the fact that this is still the third still means that it's closer to the nucleus. Okay, so Allie, on the review sheet, what do you mean by find the wavelength, frequency, speed of an electron of a given is a formula that we talked about at the beginning? Yeah, that's the same formula that we talked at the beginning, so just be able to find those. The speed is always going to be the same. The speed of light is going to be 3.00 times 10 to the 8th meters per second. Wavelength, you have that equation. Frequency, same equation, just rearrange. And then the energy, you have those other 2 equations. So it's just being able to see that idea, being able to manipulate that equation. And then also, again, the speed, the idea that all light travels at the same speed. Okay, successive ionization energies. Let's look at that. successive ionization energy. All right, let's look at one that was not in our note. So let's look at, hold on, I'm bringing up periodic table just so I have something to reference. Let's look at calcium. Now, if you look at calcium, and we have our first ionization energy. Now, I don't have the ionization energy in front of me, but if I have the first ionization energy, what I'm doing is I'm taking calcium, which is neutral at this point, and I'm supplying some amount of energy, in this case, the first ionization energy. And what I'm going to produce is calcium with a plus charge and an electron. So I'm removing an electron. Next, what I would have for this is that I could say, okay, what if I have, we'll just say this is ionization energy number 2. What if I want to remove another electron? So now I'm taking this calcium and I'm removing another electron. So now I'm going to add some more energy. And I'm going to produce another cation. Notice that my charge keeps increasing. Now, going from one to another, this amount of energy, my ionization energy 1, my ionization energy number 2, is increasing. So they always increase as we go, because what we're doing is that by removing an electron, we have now an increased number of protons compared to electrons. So actually, hold on, scrap that. I don't want to say increased number because it sounds like we're adding a proton, which we're not. But what we're doing is that by, we'll say, decreasing the number of electrons, they are held more tightly. And if we were to look at this and we were to calculate the Z effective, we would see that that Z effective also increases as well. And if that Z effective increases, what that means is that those electrons are held more tightly, so they're going to be harder to remove. Now, if you look at calcium, right when it becomes calcium with a +2 charge, this now has what we like to call a noble gas electron configuration. So it actually is going to look like its previous noble gas, which is, I believe, neon. Let me double check my handy dandy periodic table. Excuse me, argon. So now it actually looks like argon. Now removing that last electron, so now removing, say, looking at ionization energy number 3, we're removing an electron from a noble gas configuration. Noble gas configuration. Noble gas configuration. Yeah, in GC. And that's going to take a lot more energy. Not only is it a noble gas configuration, so it's not going to want to lose an electron, but also if we look at where these electrons are in the 4s energy level. This electron that we are going to try to remove is from the 3p. These electrons are closer to the nucleus. And if they're closer to the nucleus, they're going to be harder to remove because that attraction is stronger. So what you're going to see if we're trying to remove an electron from a noble gas configuration, you're always going to see a huge spike in the energy that is required. So now we have Ca2+ plus my ionization energy number 3, which is going to be like 10 times greater. This might be double, it might be 3 times, but going from here to here, because of the noble gas configuration and because those electrons are so much closer to the nucleus, huge jump. Huge jump. And so now we're going to have calcium with a 3+ charge and an electron that's left over. So, yeah. Does that make sense? I hope that does. Nicholas, is list in order of distance from nucleus? Are you talking about the list that I had on the previous slide? So going back to this, this list is in order. So as these orbitals S, P, D, F, G, those are getting further away from the nucleus. 5 is going to be lower, or is going to be further away out of nucleus than the other one. So I think that's maybe what you were talking about. Other questions? I mean, that's the idea behind ionization energy. I'm not really quite sure what else like you would need to know. I would definitely know how to do the problems that were on the homework. I think there were some questions about successive ionization. So definitely know the reasoning behind that. There were some good questions on the homework that we will definitely go over before the test tomorrow. So I will go over the homework and I will answer questions on the homework. This test coming up is shorter. I actually wrote the answer key today and it took me like 15 minutes, maybe even less to write the answer key. So this quiz actually, or this test is a lot shorter than the other ones, mostly because there's not a whole lot of math. So we do have, with that being said, we do have plenty of time before the test, at least 25, 30 minutes to go over the homework and answer any questions from the homework. So Allie, definitely look at that and see if those questions on the homework make sense, because then you will be in good shape. How many points is it out of? You know what, Daniel? I did not tally it up, but I have it right in front of me. Let's see. 14 plus 8 is 22. 37, 46. So 46 points, I believe, if I just did that math in my head right. So definitely, I don't know, that's weird because I would think that it would be less because I feel like it's a lot shorter, but yeah. It's both. I would say it's half and half, multiple choice, written answer, kind of like how all of our tests are, where the first 20, 15 or whatever are multiple choice, and then you have some show your math or write an explanation. So when you think about the test that we're going to have, even though there is some math and there is some math with the fact that you need to be able to solve like wavelength and energy and frequency and things like that. This unit is a lot more conceptual in the fact that, can you think about orbitals? Can you write out orbital diagrams? And then can you explain periodic trends? Why do we observe what we observe with our trends? So there's definitely going to be some questions like that. So make sure that you know the why behind those. Probably one of the most important ideas. Other questions? Will this be... will there be Lewis charts on the diagram? You mean drawing them? I don't know. I don't think so. But you do want to know how to do them because they're going to show up in the next unit, and they're going to show up really strongly in the next unit. So even if you don't draw them, they're still pretty important. Other questions? If we don't have any more questions, we can call it good. Again, feel free to come in tomorrow during tutorial. Feel free to ask questions then. Feel free to ask questions at the beginning of the period. We will have time. So there's definitely lots of time tomorrow before the test actually happens. Wait another minute or two to see if there's any last minute questions, but if not, we will call it good for tonight so you guys can get to studying and making sure you guys are ready. Hund's rule. You will need to know how to apply Hund's rule. So for example, if I gave you an orbital energy diagram or something like that, you would need to know how to fill it in. So for example, say that you're filling in electrons. Hold on, let me grab my pen. Let's say that you're filling in, you had your 3p orbital and you had filled in the rest of them and you wanted to put in, say, 4 electrons into the 3p. You want to remember, according to Hund's rule, that each one needs to have 1 before you pair up the other ones. So you don't need to know it by name. So you don't need to know like, oh, Hund's rule says blah, 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 blah. But you do need to know how to apply it. So you do need to know the fact that we would not have this configuration. We would have this configuration. So again, don't have to know the names by, or you don't have to know them by name, but know how to apply them. Daniel, I suggest studying everything in Unit 5. I hope that answers your question. No, I mean, I think that the 3 main things in this idea is waves and those calculations, electron configurations, and periodic trends. I would say those are kind of like the 3 big topics. I feel like the test is pretty evenly split between those 3 topics. So it just depends on where you feel like you need to focus on. I do know that you did pretty well on the quiz, so I feel like you have a pretty good grasp on the first 2. So I would definitely just focus on periodic trends if you feel like you have the other 2 ideas. Well, we actually need to draw the orbital diagrams with the squares on the test. You're not going to have to draw them like for points, but there is a question that you will have to kind of sketch one out or something like that in order to answer the problem. And that's all I'm going to say about it, but it's a multiple choice problem. So again, you're not going to have to draw it out for points. It doesn't have to be pretty, but you're going to want to sketch one out so that you can answer one of those questions. I don't think you could answer the questions without sketching one out. And actually, when I did my answer key, I sketched one out off to the side to make sure I answered it correctly. Do we subtract the electrons from the highest subshell or the highest energy subshell? For shorthand notation, and it's a positive ion. I think your example or your question comes from something like this. So let's say that we're talking about a 4s and a 5d8. Yeah, those are tricky. So if you have something like a 4s and a 5d8, you usually remove them from the highest energy one first. And I want to say that on the test, I will accept either answer. So for example, let's say that we're looking at calcium with no, not calcium. That's not going to work. Let's just go with his example that he has. So he says, let's say if we have a configuration where the last thing is 5s2, 4d8, and we wanted to create a cation, which has a +2 charge. I'm just going to put X for some atom. So where do we remove those electrons from? So one thing that I can know about this atom before even moving on is that this atom would be a transition metals. This would be 8 over in that 4th D row. It has 2 valence electrons because valence electrons we're always talking about the highest, the one that's furthest away. So the 5s is going to be the furthest away. So we're talking about those 2 electrons. So now if we look at this and we're saying, okay, so which ones do we remove? And I have a hard time answering this one just because depending on what source you look at, I've actually seen two answers. So if you write either one, I will accept it. So say that you said 5s2 4d6. I would accept that. What you do need to do is that you need to still say that this has 2 valence electrons. If you say that it's just 4d8 and we remove these electrons, this has 0 valence electrons. So again, I'm going to accept either one, but if it has a question about valence electrons, and this is where I think I marked off questions on the quiz, you need to say how many valence electrons it has because we are removing them from different levels. Yeah. All right. Well, I think that one of the reasons why maybe this review's gone faster than the other ones is because there's really not as much math in this unit than some of the other ones. Again, it's a lot more conceptual, I feel like, than math-driven. So I think that's definitely one of the reasons why we're getting this material a lot faster. All right, so I'm going to go ahead and call it good. I'm going to log off and get to grading a bunch of other stuff that I want to get graded. So feel free again to come to tutorial tomorrow with your questions. I will try to have I will definitely have time to answer them. And of course, there will be time to answer questions at the beginning of the period as well. So good luck studying, and I will see you guys tomorrow.